Welcome to Unit 6, Inference for Categorical Data with an emphasis on proportions. This is topic 6.11 or 6.11, carrying out a test for the difference of two population proportions. So hopefully we've learned all the different steps that we got to go through and now we're ready to put it into motion. So in this video, we're going to look at two examples. The first example deals with coral reefs. For a long time, scientists have believed that the proportion of diseased coral reef in the Pacific Ocean is equal to the proportion of diseased coral reef in the Atlantic Ocean. Jake, a marine biologist, believes that there is a difference between the proportion of diseased coral reef in the Atlantic Ocean and the proportion of diseased coral reef in the Pacific Ocean. So to, kind of really prove that he's right, he selects a sample from each ocean. In the Pacific Ocean, 320 coral reef were examined, 48 were diseased. In the Atlantic Ocean, 280 coral reef were examined and 52 were diseased. Conduct a test at the 1% significance level to see if there really is a difference or there really is evidence to support Jake's belief that there is a difference. So before I do any steps, the first thing I usually like to do is just kind of get my data organized. And that's just making sure we understand that we got two samples here. So the first sample is from the Pacific Ocean, and that sample had 320 coral reef, and of those 320 coral reef, it said that 48 were diseased. So 48 divided by 320 is a nice, perfect, we love it when this happens, 0.15 or 15%. Then we had a sample from the Atlantic Ocean, and this was a sample of 280 coral reef, and of those 52 were diseased. So we have 52 divided by 280, and we get not such a nice number, but we're going to round this to 0.186. Okay, so about 18.6%. So the first thing that I notice is, well, there is in fact a difference. And I kind of always like to get a positive difference, but it really doesn't matter. You can go to any order you want, to be honest. But if I do the Atlantic sample minus the Pacific sample, I do get, well, that's a terrible writing there. If I do the Atlantic sample minus the Pacific sample, I get a difference of 0.036. So the first thing I notice is, oh my gosh, there is a difference. Maybe Jake's right. But then I said, well, hold on a second. Listen, I've learned one thing in this class, and that is that samples vary. So just because I am seeing a difference between two samples doesn't necessarily mean that there is really a difference. I could just be seeing this difference because of sampling variability. So some kids like to take a moment to kind of guess what they think might happen, but 3.6%, I mean, it's not a teeny tiny difference, but it's also not really big. So I don't know, I'm kind of split, I'm not really quite sure what's going to happen. Well, that's the whole reason why we need to do the test, to make a decision on what's actually true. Is there really a difference or is there no difference? So step one is really kind of a formality. It's stating the name. This is a two-sample z-test for the difference in the proportion of diseased coral reef in the Pacific Ocean and the Atlantic Ocean. So my null is that status quo. Everything we believed is true, still true, no difference. Pacific Ocean is equal to the Atlantic Ocean. The proportion of diseased coral reef in each ocean is exactly the same. Now, I don't know what that number is, 80%, 80%, 90%, 90%, 5%, 5%. I don't really care, but I believe it's the same. And the alternative is what Jake believes. Jake truly believes that there is a difference. Jake never said that he thought that one ocean was higher or lower than the other. He just truly believes that there is a difference, which is not equal to. So this is called a two-sided test. So the big thing is at the end, we're going to have to double our p-value. All right, so now we're going to move on to step two. Step two is really nice and simple, but it does take a little bit of time because we got to write out all those conditions. So in order for us to build a sampling distribution based on the null being true that there is no difference, I got to run through my conditions. So the samples of coral reef from the Pacific Ocean and Atlantic Ocean are random to avoid bias. The sample from the Pacific Ocean is under 10% of all coral reef in the Pacific Ocean, and the sample of 280 from the Atlantic Ocean is under 10% of all coral reef in the Atlantic Ocean to assume independence. And I also need to make sure that each sample had 10 successes, diseased coral reef, and 10 or more failures, non-diseased coral reef. We don't really use the word success or failure in a problem. We just define it, right? So there's 48 diseased coral reef, 270 not, 272 not, 52 in the Atlantic Ocean disease, 228 not. Both of those numbers are much bigger than 10, so the sampling distribution is going to be normal. All right, so now we got to talk about the mean and the standard, well, I wish I could use standard deviation, but I find out I can't, but the mean and the standard error of the sampling distribution. Well, first is the mean. Now, please use proper symbols, right? A lot of kids don't want to use proper symbols. We're talking about the mean of all possible differences between the Pacific and the Atlantic Ocean. And Listen, I get that some differences are going to be positive, some are going to be negative. Sometimes the Atlantic's more, sometimes the Pacific's more. That's what happens when you sample, right? Things vary. But I'm going to go ahead and assume that the average mean of all those samples is going to be, well, 0. Because if the null's true and that these two proportions are equal, then the null's going to be 0. The mean's going to be 0. So at the end of the day, I don't know what these values are. Could be, again, could be both be 15%, could both be 30%, I don't know. But I do know that if they're both the same, you're going to get a mean of 0. Next comes standard error. Now remember, I got to use my standard error combined. If I truly believe the null is correct and that there is no difference, why don't we just combine both my samples together? And this is where we get p hat combined. So I have 100 total diseased coral reef. Who cares where they're from? I have 600 total coral reef. Who cares where they're from? So 100 divided by 600 is 0.16. Meaning that if there truly is no difference between my two samples, then why don't I just say there's 16.7% diseased coral reef? So now when I've used my standard error formula, I'm going to use that same number here and here. So my numerators are going to be exactly the same. The opposite of 0.167 is the 0.833. So my numerators are the same. The only thing is different is, my sample sizes are different. 320 from Pacific, 280 from the Atlantic. All right, there's a couple other versions of this formula that I showed you guys in the previous video, but this is the one that I like. It's easy to type into the calculator because you really don't need any parentheses. And we get a standard error combined of 0.0305. All right, so now we're ready for step 3, which is my favorite step, finding the z-score and the p-value. Once again, here we do have to be very diligent to use proper notation here. So a z-score is the observed difference, the difference I saw between my two samples, which was 0.036, minus the 0, right? Well, I assumed the mean, right? You always subtract the mean, but I'm assuming the mean is 0 because I'm assuming there is no difference. So obviously, minus 0 is 0.036. And then I'm going to divide by my standard error, and I get a z-score of 1.1803. Now, if you learned enough about z-scores, you should know that is not a very high z-score. So you should kind of already know where this problem is headed because that's not a really high value. Now comes the p-value. Please remember the definition of a p-value is so important for you to understand. It is the probability of any other difference between two samples being more extreme, meaning higher, than my sample difference of 0.036. So that is going to be equal to a z-score being greater than my z-score of 1.1803, which I need a normal CDF to find. Don't forget, you do have to double that by 2 because of our not equal to alternative. This is a two-sided test. So once you double that value by 2, you do get a p-value of 0.2379. So take a moment and soak all that in. Pretty simple work here. Now remember, what this is saying is that the probability of seeing my sample or more extreme, assuming the null is true, is actually pretty likely, which means it's not a weird sample. So I'm sorry, I don't have significant evidence. Well, actually, Jake does it. So my conclusion, making sure that I compare to my alpha level. Since my p-value of 0.2379 is greater than my alpha of 0.01, that's my significance level I asked you to use, I will fail to reject the null. There is not enough significant evidence to say that there is a difference between the proportion of diseased coral reef in the Pacific Ocean and the Atlantic Ocean. I'll be honest, guys, a lot of kids get to the conclusion and they just get lazy. They get tired and they don't want to write a nice conclusion. Please make sure you compare your p-value to your alpha level. Here it's greater than. Make sure you either reject or fail to reject. Here I'm going to fail to reject. And then make sure you give a nice contextual answer. Hey, not enough evidence that the proportion in each oceans that are diseased is any different. So at the end of the day, don't ever say, I have confirmed the null to be true. We don't word it like that. We just say, well, Jake was hoping to find a difference, but it turns out he doesn't have enough evidence to show that. All right, now we're going to move on to the second example. The CEO of a toy company is very concerned that the proportion of defective toys produced during the night shift is higher than the proportion of defective toys produced during the day shift. So to test this claim, he kind of almost does an experiment where he goes and gets 500 toys from each shift, day shift, night shift, random toys. And from each sample, he looks at how many are defective. From the day shift, 37 were defective. From the night shift, 62 were defective. Now we need to run a test to determine if there really is a significant evidence that the proportion of defective toys produced by the night shift is greater than the day shift. Now notice I did not give you a level of significance. So you could actually use either 1%, or 5%. It's completely up to you if I don't give it to you. So let's just kind of get organized here. So I have the day shift. Remember, 500 toys from the day shift, 37 were defective. I'm always hoping for nice, solid numbers. Might not always get it, though. I get 0.074. So about 7.4% of the toys from the day shift were defective. What about the night shift? All right, let's look at the night shift here. The proportion from the night shift. Out of the 500 toys that they grabbed from the night shift, 62 are defective. And that is 0.124. So the first thing I notice is that there clearly is a difference. And I always like to do it in an order that gets me a positive number. So night shift minus day shift is 0.124 minus 0.074 is 0.05. Works out to be exactly a 5% difference. So the question is this. I totally know that samples are allowed to vary. So maybe there really is no difference. Maybe that these samples are just varying a little bit because that's the one thing samples do well. Maybe I'm seeing a 5% difference because they're, it's just sampling variability. There's no difference. Or maybe there really is a difference. And the night shift really does produce a larger proportion. The only way I'm going to answer this for sure is to perform a test. So this might be a good opportunity for you to pause the video, do all the work on your own, see if you get it right, or you can just follow along. Step one is to really kind of define what I'm doing. This is a 2-sample z-test for the difference in the proportion of defective toys produced by the night shift and day shift. My null has to be that, nope, no difference. They're exactly the same. Don't know what that is. 8%, 8%, 9%, 9%, who knows? I just know that they're the same. The alternative is that the night shift really does produce a larger proportion than the day shift. All right, now comes step 2, the fun part, right? Got to make sure that everything is random to avoid bias. Got to make sure that each sample is under 10%. Now, I don't know that for sure. I don't know how many toys this company produces. So I'm just going to have to go and use the word assume. I assume that 500 from each shift is under 10% from each shift so that we can assume independence. Each shift did have enough successes and failures. Night shift had 62 defective, 43 not, 438 not. Day shift 37 defective, 463 not. Sampling distribution is going to be normal. All right, please make sure we use proper notation here. The mean of all possible sample differences should be 0. Because remember, if there's no difference, if I'm assuming that all is true, it's going to be 0. Now, to find that standard error, I do have to go ahead and combine my samples together, right? Because there's supposedly no difference, so why don't we combine them? 99 total defective toys. Who cares what shift they were from? 1,000 total toys. Who cares what shift they were from? That's a 0.099 proportion. So when I go and find my standard error, I'm going to use that same p-hat combined in both numerators and the opposite, 0.901 in both numerators. In fact, my denominators are even the same because my sample size are exactly the same. But regardless, type that into your calculator, standard error of 0.0189. Z-score time. All right, Z-score is taking your difference that we observed, 0.05 between our two samples. Minus 0 doesn't really do anything, but I got to subtract the mean. There is assumed to be no difference. And I'm going to divide by that standard error combined, 0.0189. Now, that is a pretty high score. That is a pretty high Z-score. I recognize high Z-scores. 2.64 is getting pretty high. So now I got to find the p-value. It's the probability that a sample is more extreme than mine. Any other sample from day shift to night shift is going to be more than mine, 5%. That's a Z-score greater than 2.6455. Use normal CDF, 0.0041. That's pretty low. Now that means the probability of my sample occurring or more extreme is pretty unlikely, assuming the null is true. But guess what? It did, in fact, happen. So since something very significant happened, I'm going to go ahead and reject the null. So since my p-value 0.0041 is less than my alpha, 0.01, I'll reject the null. There is significant evidence that the proportion of defective toys produced by the night shift is greater than the proportion of defective toys produced by the day shift. So I definitely, the CEO definitely has evidence that the night shift produces more. I know that in some people, my grandma might say, oh, 5% is not really a big deal. Well, I just proved it is. A 5% difference is a big deal, and that does prove that the day shift has less proportion of defective chips, or defective parts, toys, than the night shift. All right, guys, so hopefully these examples make sense. I mean, I go through this pretty slowly, but I also hope that you understand it's pretty easy. Yeah, it's a little bit of writing, especially with these conditions and stuff, but overall, it really should make a lot of sense. Hope you liked it, hope you understood it, and ready for the next video. See you soon.